The thermometer outside read 9 degrees below zero. Inside Martin Vogel's cabin, in the Wind River Range of Wyoming Territory in February of 1883, the mercury showed 71 degrees Fahrenheit. 71 degrees, the kind of temperature that made a man comfortable in his shirt sleeves, the kind of warmth that seemed impossible in a frontier cabin during a brutal mountain winter. But what was even more impossible, what made every visitor stare in disbelief and concern, was the stovepipe. It was wrong. Completely, obviously, dangerously wrong. The pipe that should have carried deadly smoke and carbon monoxide safely out of the cabin didn't go straight up through the roof like every proper stovepipe in Wyoming Territory. Instead, it wound through the cabin in a serpentine pattern, running horizontal for 10 feet, then up 2 feet, then horizontal again, zigzagging back and forth like a drunk snake, with visible gaps and openings along its length. Smoke leaked from these gaps. Heat radiated from every section of the convoluted path. The whole assembly looked like it had been installed by someone who had no idea what they were doing. Or worse, by someone with a death wish. Martin's neighbor, a rancher named Frank Jessup, stood in the cabin staring at the stovepipe with horror and fascination. He'd come to check on Martin, worried that the foolish modifications Martin had made to his heating system had killed him. Instead, he found Martin alive, comfortable, and sitting by a small fire that barely qualified as burning. "Martin," Frank said slowly, "you're going to die. That pipe is leaking smoke into your cabin. You're breathing poison. Can't you see it? Can't you smell it?" Martin looked up from the book he was reading and smiled slightly. "I can see the smoke. But I am not breathing poison. Watch." He walked over to one of the gaps in the pipe and held his hand near it. "Feel this. The heat coming from this section alone could warm a small room. Now smell." He gestured toward the air in the cabin. "Do you smell coal smoke? Wood smoke? Carbon monoxide has no smell, but smoke does. Do you smell any?" Frank breathed deeply, confused. He smelled nothing. The air was clear, warm, and fresh, but the pipe was obviously leaking. He could see wisps of what looked like smoke or steam coming from the gaps. How is that possible? If the pipe is broken and smoke is leaking, where is the smoke going? Martin's smile widened. "The pipe is not broken. It is designed exactly as I intended. What you see leaking is not smoke, it is water vapor. And the reason you smell nothing dangerous is because there is nothing dangerous. Every bit of smoke and gas that could hurt me goes outside. What stays inside is only heat. Pure, clean, radiant heat." Frank stared at him. "That's impossible. You can't separate smoke from heat. They come together from the fire. They leave together through the pipe. That's how stoves work." Martin walked over to his small fire and adjusted a damper. "That is how most stoves work, yes, and that is why most stoves waste 80% of their heat up the chimney. My stove wastes almost nothing. Every bit of heat that can be extracted, I extract. The smoke goes outside. The heat stays inside. And my cabin stays at 71 degrees while burning 1/4 the wood you burn to keep your cabin at 55. What Martin Vogel had created was something that looked so wrong, so dangerous, so poorly constructed, that every person who saw it predicted it would kill him through smoke inhalation or carbon monoxide poisoning. Local ranchers made bets on how long Martin would survive before being found dead in his cabin. Some gave him a week, others, more optimistically, gave him a month. They all agreed he was insane, that his modifications violated every principle of safe stove operation, and that his folly would end in tragedy. But February turned to March, March to April, and Martin remained alive, healthy, and warmer than anyone else in the Wind River Range. His broken stovepipe, the death trap that everyone swore would kill him, was actually the most efficient heat extraction system anyone in Wyoming had ever seen. And the story of how he built it, why it worked, and why everyone was so convinced it would fail reveals fundamental misunderstandings about heat, combustion, and the difference between looking wrong and being wrong.
Martin Vogel was not a typical Wyoming rancher or homesteader. Born in Bavaria in 1844, he'd been trained as a mechanical engineer, working on steam locomotives and industrial boilers in Munich before immigrating to America in 1872. He understood thermodynamics, heat transfer, and combustion efficiency better than almost anyone on the frontier. He'd spent 10 years working for the Union Pacific Railroad, maintaining and improving steam locomotives before deciding he wanted a quieter life. In 1880, at age 36, Martin filed a homestead claim in the Wind River Range and built a cabin. The location was beautiful but brutal. Winter temperatures regularly dropped to 20 below zero. Wind was constant. Firewood, while available, required significant effort to cut and haul. Martin, looking at his first Wyoming winter ahead, decided he would not spend it the way most settlers did, burning massive amounts of wood to achieve minimal comfort. He would engineer a better solution. The problem, as Martin saw it, was that conventional wood stoves were grotesquely inefficient. A typical cast iron stove burned wood, generated heat, and immediately sent 80 to 90% of that heat up the chimney along with the smoke. The stove itself radiated some heat into the room, perhaps 10 to 15% of the total energy in the wood. The rest was wasted. Martin knew from his locomotive work that combustion gases exiting a boiler often carried temperatures of 600 to 800 degrees Fahrenheit.
All that heat gone up the stack, doing no useful work. If you could extract that heat before the gases escaped, you would multiply your heating efficiency several times over. The challenge was doing so safely. Smoke and combustion gases contain carbon monoxide, carbon dioxide, creosote, and other nasty compounds. If you slow down the exhaust or route it through the living space, you risk poisoning the occupants or creating dangerous creosote buildup that could cause chimney fires. Every conventional stove design prioritized safety by getting the exhaust outside as quickly and directly as possible. Efficiency was sacrificed for safety. Martin believed there was a way to have both. He began by studying exactly what came out of a wood fire. Combustion produces heat, water vapor, carbon dioxide, carbon monoxide if combustion is incomplete, various particulates and gases, and creosote vapors that condense when cooled. The dangerous components are carbon monoxide and creosote. Carbon dioxide is not toxic in the concentrations produced by a wood fire, though it can displace oxygen in a completely sealed space. Water vapor is harmless. Particulates are irritating, but not immediately dangerous in small quantities. The key insight was that temperature mattered. Carbon monoxide is produced by incomplete combustion, which happens when fires burn too cool or don't get enough air. A hot, well-supplied fire produces mostly carbon dioxide and water vapor, with minimal carbon monoxide. Creosote condenses when smoke cools below approximately 250 degrees Fahrenheit. If exhaust temperature stays above 250 degrees throughout the entire exhaust path until it exits outside, creosote won't condense inside the system. Martin's design would ensure complete combustion in a hot firebox, eliminating carbon monoxide. It would extract heat from the exhaust gases by running them through a long, convoluted path that transferred heat to the cabin, but it would keep exhaust temperature above 250 degrees throughout that path to prevent creosote condensation. And it would ensure that combustion gases, even though cooled significantly, still exited outside, never mixing with cabin air. The trick was separating the heat energy from the gas itself. He built his system in the fall of 1882, working alone, fabricating components with tools and materials available in the nearest town, 50 miles away. The stove itself was a standard cast iron wood stove, nothing unusual, but the exhaust pipe was anything but standard. Instead of a simple 6-inch diameter pipe going straight up through the roof, Martin constructed a complex heat exchanger. The exhaust exited the stove into a 6-inch pipe that immediately entered a larger, 10-inch diameter outer pipe.
The 6-inch pipe ran through the center of the 10-inch pipe for a distance of 10 feet horizontally across the cabin. The space between the inner 6-inch pipe and the outer 10-inch pipe was sealed at both ends but vented to the cabin air through small holes along the top of the outer pipe. This created a double-wall pipe. Hot exhaust ran through the inner pipe. Cabin air circulated through the gap between pipes, heated by contact with the hot inner pipe, and then vented back into the cabin through the holes. The exhaust continued through the inner pipe, never mixing with cabin air, but the heat from that exhaust warmed the cabin air flowing through the outer jacket. After the first 10-foot horizontal section, the inner pipe turned upward for 2 feet, still jacketed by the outer pipe. Then it turned horizontal again for another 10 feet, running parallel to the first section but 2 feet higher. This pattern repeated 4 times. The exhaust pipe zigzagged back and forth across the cabin in 4 horizontal runs, each one 10 feet long and 2 feet higher than the previous run. The total path length through the cabin was 40 feet. 40 feet of contact between hot exhaust gases and cabin air, separated by the inner pipe wall. By the time the exhaust reached the final turn and headed up through the roof to exit outside, it had given up most of its heat. Martin calculated that exhaust entering his heat exchanger at 700 degrees would exit at approximately 300 degrees, still hot enough to rise and draft properly, still hot enough to prevent creosote condensation, but 400 degrees cooler. 400 degrees of heat transferred to the cabin instead of wasted up the chimney. But the system had one feature that looked absolutely insane to anyone who saw it. The outer jacket pipes, the 10-inch diameter pipes that surrounded the exhaust pipe, had visible gaps at the joints. These gaps were intentional. They allowed cabin air to enter the space between the pipes, get heated, and exit back into the cabin. But to someone unfamiliar with the design, these gaps looked like leaks. It looked like the pipe was broken, poorly assembled, and leaking smoke into the cabin. Martin had tried to explain this to the neighbors who helped him install the system. The gaps are deliberate. They allow air circulation. The smoke stays in the inner pipe. Only heat escapes through these gaps, along with some water vapor from condensation. But his explanations made little sense to men who'd never seen anything like this design. They saw gaps in a stovepipe. Their instinct, based on years of experience with conventional stoves, told them this was deadly dangerous. When Martin fired up the system for the first time in November of 1882, neighbors who'd heard about his strange stovepipe came to watch. Some came out of curiosity. Others came out of concern, ready to rescue Martin if he started showing signs of carbon monoxide poisoning. Martin loaded his stove with well-seasoned pine, adjusted the air intake to ensure hot, complete combustion, and lit the fire. The fire burned hot and clean. Smoke entered the heat exchanger system and began traveling through the 40 feet of pipe. Within minutes, heat began radiating from every section of the pipe. The outer jacket pipes grew warm, then hot. Air began circulating through them, heated by the inner exhaust pipe, and venting back into the cabin through the gaps. To the neighbors watching, it looked like smoke was pouring from gaps in the pipe all over the cabin. A rancher named Tom Peterson grabbed Martin's arm. "Martin, for God's sake, your pipe is falling apart. Smoke is everywhere. You need to put out that fire before you kill yourself." Martin remained calm. "That is not smoke. That is water vapor. When combustion gases cool, water vapor condenses into visible mist. It looks like smoke, but it is harmless. Watch." He walked to one of the gaps and thrust his face directly into the escaping vapor, breathing deeply. "If this were smoke, I would be coughing. My eyes would be burning. I would smell wood smoke. I smell nothing. I feel nothing but warm, moist air. Try it yourself." Peterson, convinced Martin was already affected by carbon monoxide and not thinking clearly, refused to approach the gaps. Several other neighbors stood near the door, ready to leave quickly if conditions worsened. But over the next hour, something became undeniable. The cabin was getting dramatically warmer. The temperature rose from 45 degrees to 55 degrees to 65 degrees. The fire in the stove was moderate, not roaring. Wood consumption was minimal. Yet heat poured into the cabin from every section of the 40-foot heat exchanger. Martin had installed thermometers at various points. The exhaust entering the heat exchanger registered 680 degrees. The exhaust exiting through the roof registered 320 degrees. 360 degrees of heat extracted from the exhaust. 360 degrees that would normally have been wasted. Peterson, still skeptical and concerned, asked the obvious question. Even if that vapor is harmless, how do you know the smoke isn't leaking? How do you know you're not breathing carbon monoxide? Martin had anticipated this question. He'd brought a canary from town, a bird used in mines to detect deadly gases. If carbon monoxide were present in dangerous quantities, the bird would show distress before humans. The canary sat in its cage, chirping happily, showing no signs of distress even as the cabin warmed and the system ran for hours. Peterson watched the bird. He felt the heat radiating from the pipes. He observed that Martin showed no signs of poisoning, no headache, no confusion, no symptoms of smoke inhalation. Slowly, reluctantly, he began to accept that maybe, just maybe, Martin's insane-looking stovepipe actually worked. By evening, the cabin temperature had stabilized at 68 degrees. Martin's fire had burned down to coals. He added 4 small splits of wood, just enough to maintain gentle heat. The cabin stayed warm. The heat exchanger continued pulling warmth from the moderate exhaust. The next morning, after running the system through the night, Martin was alive, healthy, and the cabin was still 65 degrees, despite outside temperatures dropping to 15 below. His wood consumption for the entire night and morning was approximately 1/8 of what a conventional stove would require for the same heat output. Word spread quickly. That crazy German had built a stovepipe that looked like it was falling apart, but somehow kept his cabin warmer than anyone else's cabin while using almost no wood. Some people said it was witchcraft. Others said it was luck and would fail eventually, probably catastrophically. But as November turned to December and December to January, Martin's system continued working flawlessly. His cabin stayed consistently between 65 and 71 degrees. His wood consumption remained minimal, and he remained alive and healthy, with no signs of carbon monoxide poisoning. The skepticism began to shift. A few brave souls asked Martin to explain exactly how his system worked and why it was safe. Martin, happy to share knowledge, invited small groups to his cabin for demonstrations. He showed them the double-wall pipe design. He explained how the inner pipe carried exhaust safely outside while the outer jacket captured heat. He demonstrated with smoke tests that no combustion gases entered the cabin air. He showed temperature measurements at various points in the system. He explained the principles of heat exchangers, convection and condensation. Some people understood, many didn't. But the results were undeniable. Martin's system worked. By February of 1883, 3 neighbors had asked Martin to help them build similar systems. He agreed. The first installation was for Frank Jessup, the rancher who'd been so horrified by Martin's broken-looking stovepipe. Jessup had spent January burning 3 cords of wood and keeping his cabin at barely 55 degrees. He was exhausted from cutting and hauling wood, and his supply was running dangerously low. He swallowed his pride and asked Martin for help. If you're fascinated by these forgotten innovations that solved real problems with clever engineering, this is exactly the kind of content we create. Please take a moment to subscribe to this channel and hit the notification bell. We dive deep into historical techniques that could still teach us about efficiency and problem-solving today. Your subscription helps us continue bringing you these stories. Now let's explore the science behind why Martin's broken-looking stovepipe worked so brilliantly. The physics of Martin's heat exchanger system operates on principles that modern engineers would recognize immediately as counterflow heat exchange, one of the most efficient methods for transferring heat between 2 fluids or gases. First, the concept of a heat exchanger. A heat exchanger is any device that transfers heat from one medium to another without mixing them. Car radiators are heat exchangers. Air conditioner coils are heat exchangers. Martin's double-wall stovepipe was a heat exchanger transferring heat from hot exhaust gases to cabin air without allowing them to mix. The efficiency of a heat exchanger depends on surface area, temperature difference, and contact time. Martin's 40-foot pipe length provided enormous surface area. The temperature difference between 700-degree exhaust and 60-degree cabin air was substantial, and the serpentine path ensured long contact time. Second, the principle of convection. Hot exhaust in the inner pipe heated the pipe wall. The pipe wall heated the air in the gap between inner and outer pipes. This heated air, being less dense, rose and exited through the gaps at the top of the outer pipe. Cool cabin air was drawn into the bottom of the gap to replace it. This created a natural convection current, circulating cabin air through the heat exchanger continuously without any mechanical pumps or fans. The system was entirely passive, driven by temperature differences alone. Third, the separation of heat and combustion products. This is the key insight that made Martin's system safe. Heat is energy. It can be transferred through conduction, convection, and radiation. Combustion products are molecules, carbon dioxide, water vapor, etc. Martin's inner pipe conducted heat from the exhaust to the pipe wall. The pipe wall radiated and conducted heat to the air in the gap, but the molecules of combustion gas remained contained in the inner pipe and exited outside. The heat energy was extracted, but the gases themselves never entered the cabin. This separation is possible because heat and matter are not the same thing. Heat can move through a solid barrier. Matter cannot. Fourth, preventing creosote condensation. Creosote forms when smoke cools below approximately 250 degrees Fahrenheit. In a conventional stovepipe, the pipe is usually single wall, exposed to cold outside air. The exhaust cools rapidly. Creosote condenses inside the pipe, and over time this creates dangerous buildup. Martin's inner pipe was insulated by the outer jacket and the air gap. The exhaust cooled more slowly, in a controlled manner. By the time it exited through the roof, it was still above 300 degrees, well above creosote condensation temperature. The 40-foot path extracted heat without cooling the exhaust too much. This was a delicate balance. Extract too much heat and you risk creosote. Extract too little and you waste energy. Martin's calculations, based on pipe diameter, length, and estimated flow rates, hit the sweet spot. Fifth, ensuring complete combustion. Carbon monoxide is produced by incomplete combustion, typically from fires that burn too cool or lack sufficient oxygen. Martin's stove design included adjustable air intakes that he set to provide excess air for complete
combustion. His hot firebox with temperatures exceeding 1,000 degrees ensured that wood burned completely, producing primarily carbon dioxide and water vapor. Tests with his canary confirmed no dangerous carbon monoxide levels. Modern carbon monoxide detectors would later validate that properly operated wood stoves with adequate air supply produce minimal CO. The mathematics of heat extraction are straightforward. Exhaust gases have a specific heat capacity of approximately 1 kilojoule per kilogram per degree Celsius. Martin's stove produced approximately 0.05 kilograms per second of exhaust when burning at moderate rate. Cooling this exhaust by 400 degrees from 700 to 300 extracted approximately 20 kilowatts of heat. That's roughly 68,000 BTUs per hour. A typical home furnace produces 40 to 60,000 BTUs per hour. Martin's heat exchanger was capturing the equivalent of a small furnace's output from what would otherwise have been waste heat. A conventional stovepipe would have sent that 20 kilowatts up the chimney, wasted. Martin captured it and used it to heat his cabin. This explains why his cabin reached 71 degrees, while neighbors' cabins struggled to reach 55 degrees. He was extracting and using heat that others were throwing away. The visible vapor that looked like smoke was indeed just water vapor. Combustion of wood produces significant amounts of water.
When exhaust gases cool below the dew point, this water vapor condenses into tiny droplets, creating visible mist. This is the same phenomenon that creates clouds in the sky or fog on cold mornings. Harmless water droplets suspended in air. The gaps in the outer jacket allowed this water vapor to escape rather than accumulating and dripping inside the pipes. If Martin had sealed the outer jacket completely, condensation would have collected and eventually caused rust and water damage. The gaps served dual purposes, allowing air circulation for heat transfer and allowing water vapor to escape. Modern heat exchangers face the same condensation challenges and use similar venting strategies. The design principles Martin used are now standard in high-efficiency furnaces, which extract so much heat from exhaust that condensation occurs. These condensing furnaces achieve 90 to 95% efficiency, compared to 60 to 70% for non-condensing furnaces. Martin's system was probably achieving 80 to 85% efficiency, far better than conventional wood stoves at 10 to 20%. He was decades ahead of his time. The safety concerns his neighbors expressed were not entirely unfounded. A poorly designed heat exchanger could indeed create dangerous conditions. If the inner pipe developed a leak, combustion gases could mix with cabin air. If the system overcooled the exhaust and creosote accumulated, a chimney fire could result. If combustion was incomplete, carbon monoxide could reach dangerous levels before being detected. Martin avoided these dangers through careful design, quality construction, and proper operation. He used heavy-gauge steel pipe for the inner exhaust pipe, welded at all joints to ensure no leaks. He calculated the heat extraction carefully to prevent overcooling. He maintained hot, clean burns with adequate air supply. And he monitored the system constantly during the first months of operation, ready to shut down if any problems developed. No problems developed. The system worked as designed. By March of 1883, when Frank Jessup found Martin's cabin at 71 degrees and initially thought the broken pipe would kill him, the system had been operating flawlessly for 4 months. Jessup's horror turned to fascination as Martin explained the engineering. Jessup became one of the system's earliest adopters, and his cabin that spring gained its own broken-looking stovepipe that his neighbors warned would kill him. It didn't. It kept him far warmer than he'd ever been during a Wyoming winter. The spread of Martin's design was slower than it might have been because the system looked wrong. Even when people understood intellectually that it was safe and effective, the visible gaps and the escaping vapor triggered instinctive concern. This is broken. This is leaking. This is dangerous. Overcoming these instincts required trust in Martin's engineering, and trust was hard to build. Some people never built trust. They continued using conventional stoves, burning far more wood, achieving far less comfort but feeling safe because their stovepipes looked right. The appearance of safety mattered more than actual safety or efficiency. Other people, pragmatic and willing to learn, overcame their instincts. By 1885, approximately 20 cabins and homes in the Wind River region had Martin-style heat exchangers. Each installation was custom-built for the specific stove and cabin layout. Some used 3 horizontal runs instead of 4. Others used 5. Some builders modified the design, adding dampers or adjustable vents, but the core principle remained: extract waste heat from exhaust, using a double-wall pipe heat exchanger before the exhaust exits outside. Results were universally positive. Fuel consumption dropped by 50 to 75% compared to conventional stoves. Cabin temperatures increased by 10 to 20 degrees. Comfort improved dramatically, and nobody died from carbon monoxide poisoning or smoke inhalation. The systems worked. Martin himself continued refining his design over the years. In 1884, he added a water heating coil. A copper pipe ran through one section of the heat exchanger, and water circulating through this pipe was heated by the exhaust. This provided domestic hot water for washing and cooking without requiring a separate water heater. In 1886, he experimented with adding
thermal mass. He built a masonry enclosure around one section of the heat exchanger, creating a heat storage battery that would retain warmth even after the fire died down. These refinements increased efficiency even further. By 1888, Martin's cabin could maintain comfortable temperatures for 24 hours after the fire went out, thanks to the thermal mass storage combined with excellent insulation and the heat exchanger. His total wood consumption for an entire winter was approximately 4 cords. Neighbors using conventional stoves burned 15 to 20 cords for similar-sized cabins. Martin's system used 1/4 to 1/5 the fuel. The economic advantage was overwhelming. At the time, a cord of wood represented approximately 2 full days of labor to cut, split, and haul. Saving 15 cords per winter meant saving 30 days of brutal physical work. That's a full month of labor saved every year. Over a decade, that's nearly a year of life not spent cutting wood. The return on investment for building the heat exchanger, perhaps 2 weeks of work and modest material cost, was immediate and permanent. But the design remained niche. It never spread beyond the local region. Several factors limited adoption. First, it required custom fabrication. You couldn't buy a Martin heat exchanger from a catalog. Each one had to be built on site, fitted to the specific stove and cabin. This required metalworking skills and tools that not everyone had. Second, it looked wrong. The psychological barrier of installing something that appeared broken and dangerous was insurmountable for many people. Even when presented with data proving safety and efficiency, the visual appearance created doubt. Third, it required understanding. To operate the system safely, you needed to understand how it worked. You needed to maintain hot, complete combustion. You needed to monitor for problems. You needed to clean the system annually. Conventional stoves were simpler to understand and operate, even if less efficient. Fourth, wood was abundant in many regions. If fuel was essentially free, available for the effort of cutting it, the incentive to build complex efficiency improvements was reduced. Only in regions where wood was scarce or the labor of harvesting it was significant did the efficiency advantages of Martin's system justify the construction complexity. By the 1890s, as the frontier era ended and industrial heating systems became available, Martin's design faded from use. New homes were heated with coal stoves, then oil furnaces, then gas furnaces. The custom-built heat exchanger systems were left behind as people moved or upgraded. Martin himself moved to Cheyenne in 1896 and worked as a consulting engineer for mining and railroad operations. He tried to interest manufacturers in producing prefabricated heat exchanger systems for wood stoves, but found no commercial interest. The market wanted convenience,
not efficiency. He died in 1914 at age 70, having lived through the transition from frontier hand-built heating systems to industrial mass-produced furnaces. His broken-looking stovepipe, the system that everyone swore would kill him, but instead kept him warmer than anyone else in Wyoming territory, was largely forgotten. But the principles he demonstrated remained valid and would eventually be rediscovered. Modern high-efficiency wood stoves use heat exchangers as a standard feature. Secondary combustion chambers extract additional heat from gases before they exit. Catalytic converters ensure complete combustion, reducing emissions and extracting maximum energy. Some advanced wood stoves achieve 75 to 80% efficiency, comparable to what Martin achieved in 1883. Modern condensing gas furnaces use heat exchangers to cool exhaust below the condensation point, extracting so much heat that water vapor condenses, hence the name. These furnaces achieve 95% efficiency by capturing heat that conventional furnaces waste. The condensate must be drained away, exactly as Martin's water vapor had to be vented. The engineering challenges Martin solved are the same challenges modern HVAC engineers solve today. We just have better materials, better tools, and 140 years of additional knowledge. But the fundamental principles: extract waste heat before it escapes, separate heat energy from combustion gases, ensure complete combustion for safety and efficiency. These principles were demonstrated by Martin Vogel in a Wyoming cabin in 1883. He didn't invent heat exchangers. The concept existed in steam engines and industrial processes, but he applied the concept to residential wood heating in a way that was unprecedented on the frontier and decades ahead of widespread adoption. The story of Martin's broken stovepipe is ultimately about the difference between appearance and reality. The system looked wrong. It appeared dangerous. Every conventional indicator said it would fail catastrophically, but appearances were deceiving. The reality was that Martin had engineered a sophisticated heat extraction system that was both safer and more efficient than conventional designs. The gaps that looked like leaks were intentional vents. The vapor that looked like smoke was harmless condensation. The convoluted pipe path that looked like poor planning was calculated for maximum heat transfer. Understanding this required looking beyond surface appearances to underlying principles. Most people couldn't or wouldn't do that. They trusted what they saw, and what they saw looked wrong. A smaller number of people, those willing to investigate, question, and learn, recognized that Martin's system was brilliant. These people adopted the technology and benefited enormously. The lesson applies far beyond stovepipes. How often do we judge innovations by appearance rather than by results? How often do we dismiss unconventional approaches because they look wrong without investigating whether they actually are wrong? How often do we choose familiar, comfortable, conventional solutions over unfamiliar, uncomfortable, unconventional solutions that work better? Martin's neighbors swore his broken stovepipe would kill him. They were wrong. It heated his cabin to 71 degrees and saved him thousands of hours of labor over his lifetime. Their certainty was based on appearances and conventional wisdom. Martin's success was based on understanding and engineering. The gap between certainty and correctness is often large. We should remember this before we swear something won't work. Before we continue with the practical lessons from Martin's work, I want to ask you to take action right now. If this story changed how you think about innovation, efficiency, or questioning conventional wisdom, please subscribe to this channel. Hit that subscribe button, turn on notifications, and join our community. We uncover forgotten knowledge that can still teach us today. Your support makes this work possible. Thank you. Now let's talk about what we can learn from Martin's broken stovepipe. The primary lesson is that heat and combustion products can be separated. Modern building codes often prohibit anything that looks like Martin's design because of safety concerns about exhaust gases entering living spaces. These concerns are valid for poorly designed systems, but properly designed heat exchangers safely extract heat while venting combustion products outside. We should distinguish between prohibiting dangerous systems and prohibiting all unconventional systems because they might be dangerous. Overly conservative regulation can prevent innovation. Second lesson: waste heat represents enormous opportunity. Martin extracted 20 kilowatts from exhaust that would otherwise have been wasted. Modern homes waste heat through hot water going down drains, through exhaust air from ventilation, through clothes dryers, through countless processes. If we systematically captured and reused waste heat, residential energy consumption could drop by 30 to 50%. The technology exists. The question is whether we design buildings to capture waste heat or continue throwing it away. Third lesson: visual appearance affects adoption more than engineering merit. Martin's system worked brilliantly but looked wrong. This limited adoption. Modern innovations face the same challenge. Solar panels, green roofs, rainwater collection systems, composting toilets, these often work better than conventional approaches but look unfamiliar or unappealing. Overcoming aesthetic bias requires education, but also requires designing systems that work well and look acceptable. Function and form both matter. Fourth lesson, custom solutions outperform standardized solutions in specific circumstances. Martin's heat exchanger was custom built for his cabin, his stove, his needs. It performed far better than a standard stove because it was optimized for his situation. Modern construction relies heavily on standardization, which reduces cost and complexity, but also reduces optimization. We've gained efficiency in construction, but lost efficiency in operation. Finding the right balance between custom and standard is an ongoing challenge. Fifth lesson, understanding principles enables innovation. Martin understood heat transfer, combustion, and fluid dynamics. This understanding allowed him to design a system that seemed impossible to people who lacked that understanding. Education in fundamental principles empowers people to solve problems in unconventional ways. We need more teaching of principles and less teaching of procedures. The practical barriers to adopting heat exchanger technology today are mostly regulatory and cultural. The engineering is straightforward. Modern materials make construction easier than in Martin's era, but building codes in most jurisdictions prohibit custom modifications to exhaust systems. Insurance companies are reluctant to cover unconventional heating. Building inspectors, trained on conventional systems, don't know how to evaluate innovative approaches. These barriers exist for good reasons, safety and reliability, but they also prevent improvements. We need pathways for testing and approving innovative systems without requiring decades-long adoption cycles. Some modern wood stoves include heat exchangers as original equipment, approved by EPA and building codes. These provide some of the benefits Martin achieved, but they're still compromises designed for mass production and broad applicability rather than optimization for specific situations. A custom-built heat exchanger for a specific installation could still outperform commercial systems, but regulatory hurdles make this impractical for most people. The economic calculation has also changed. In Martin's era, fuel cost was measured in labor to harvest it. Today, fuel cost is measured in dollars to purchase it. If wood costs $300 per cord and a heat exchanger reduces consumption from 20 cords to 5 cords, the annual savings is $4,500. At that savings rate, even a complex custom system would pay for itself in 1 or 2 years. But few people heat exclusively with wood anymore. Most use natural gas, electricity, or oil. Heat exchangers for gas furnaces already extract heat quite efficiently. The opportunity for improvement is smaller. Still, residential heating accounts for approximately 40% of home energy use. Even 10 to 20% improvements would have significant impact on energy consumption and costs. Heat recovery ventilators, which extract heat from exhaust air to preheat incoming fresh air, provide some of these benefits. But many homes still lack even this basic heat recovery. We're throwing away heat that could be captured with straightforward technology. The story of Martin Vogel and his broken-looking stovepipe reminds us that appearances can deceive, that conventional wisdom can be wrong, and that engineering principles matter more than superficial judgments. His neighbors swore his system would kill him. Instead, it kept him warmer and more comfortable than anyone else in Wyoming territory. The difference was understanding. Martin understood heat transfer. His neighbors understood only that stovepipes shouldn't have gaps. Understanding won, conventional wisdom lost. Today, we face energy challenges that require innovative solutions. We need better heating systems, better insulation, better heat recovery, better everything. The solutions won't all be conventional. Some will look wrong to people trained on current practice. We need to cultivate the ability to look past appearances to underlying principles, to evaluate innovations based on results, rather than familiarity, to be willing to say, maybe that's not broken, maybe that's better. Martin's cabin at 71 degrees in 9 below zero weather proved that unconventional approaches can outperform conventional ones by enormous margins. The question is whether we're willing to learn from that proof. Thank you for watching this story about Martin Vogel and his remarkable heat exchanger system. If you found value here, if this changed how you think about innovation and conventional wisdom, please share it with someone who might benefit. And remember, the thing that looks most broken might actually be the thing that works best. Don't judge by appearance. Judge by understanding. Don't trust certainty that's based on assumptions. Trust results that are based on evidence. Martin's neighbors were certain he'd die. They were wrong, and their certainty nearly prevented them from learning something valuable. Don't let your own certainty prevent you from investigating ideas that look wrong but might be right. Sometimes the broken stovepipe is exactly what you need.